Good. All right. Hello. Thanks for joining my talk. My name is Pat Marion. I'm a team lead at Boston Dynamics, and my group works on developing large behavior models for Atlas. So it's a pleasure to follow Ben's talk because we've already set up what large behavior models are, and we can jump in here. So what you're seeing on the left is an end-to-end neural network policy, which is mapping the images to actions. And this policy is able to control the full range of our Atlas humanoid robot. It's able to take steps, crouch down low, reach up high, control the grippers here, and control the neck to aim the head and get novel camera views. And it's doing that to complete this task here, where it's emptying this blue bin of parts and putting them into the wheeled bin there. On the right, you're seeing the same approach applied to our manipulation test stand, which is similar to the Atlas humanoid, but just the upper body only. And here, this is a single policy trained to complete a diverse set of tasks, including unfurling a tablecloth, tying a knot in a rope, and flipping over a car tire, for example. As you can see, the policy is able to be reactive. If I move the bin away with the hockey stick, then the robot notices that change to the environment and reacts with its actions to pull the bin in close. So the approach we're doing is behavior cloning, where we're going to take the binocular fisheye RGB images from the cameras on the head of the robot, as well as proprioception, so that's like joint positions and end effector poses and other robot state information, and as well as a language prompt. Put that into the neural network, which is then going to predict a trajectory of actions. And those actions are then going to be executed by the low-level controller, in our case, the Atlas Model Predictive Controller. So here's sort of a robot eye view of the policy predictions. On the right, you're seeing one of the images. The robot has two sort of stereo views here. And on the left, you're seeing a visualization of the actions predicted by the policy. This is all the videos in the stock, by the way, are at real-time speed, 1x speed. So the dots you're seeing represent the positions of end effector poses, but it is predicting full 6-DOF poses for the end effectors, the feet, and the body. And the policy is predicting and updating. So every time you see an update is a new prediction. It predicts forward a horizon of actions into the future. And the controller is going to begin executing that trajectory. And while it's executing it, we're going to get a new observation and sort of switch to the new trajectory. So behavior cloning requires a source of expert demonstrations. So we developed a whole body teleoperation system to essentially pilot the robot to carry out these tasks to record expert demonstrations. So I'm going to present the Teleop system now. This was largely developed by Kevin Bergman, who presented an even more detailed view of this earlier today at the Baymax workshop. So what you're seeing here is sort of a side-by-side view of Kevin teleoping the robot. You can see Kevin here on the right and the robot on the left. He's actually in the background too, so you can see him sort of with the robot. He's wearing a VR headset, and the VR headset is showing him the images collected from the robot's cameras. So this gives him situational awareness, and he can control the robot using 6 points of tracking. So there's trackers on his hands, on his feet, on his body, and on his head. He can crouch his body, he can sway left and right, or he can even take steps in order to complete this task. The inset view in the lower right is what he's seeing. And so in addition to seeing the view from the robot cameras, he also has a view of his own actions, which are these sort of green overlays. I'll get into those in a little more detail. Yeah.
Question. So how skilled is he at not the task, but at controlling Atlas to do the task?
It helps to have experience. Yeah. So Kevin is a very skilled teleoperator, particularly because he implemented the system. But he's not the only person that can accomplish a task like this. But if you step into the system at the very beginning, you will not be very skilled. You do need to practice tasks for a while.
It looks like he's being careful about foot, body, location, everything.
Absolutely.
And his awareness of what the robot can and can't do.
Yes.
More than him just doing what he wants to do the task.
Yep.
And then
to do a task quickly and fluidly is different from just doing a task roughly. So you can sort of stumble your way through and complete a task. But if you want to create a really nice demonstration video like this, you will want to practice and understand sort of the dynamics of the robot and the controller because you are, teleoping on top of this system. Um, so to design a teleoperation system, let's go through the requirements. First, we want a teleop system that can control the whole body to perform these tasks. So that means stepping and moving around, reaching all the way down to the ground. So that set of requirements made us make some design decisions, as well as we want the teleop system to produce a stream of commands which are learnable by the policy. So you can make a very complicated teleop system, but you want to make sure your teleop command stream is aligned with your action space that the policy is actually going to be able to learn. So at the top left, you're seeing Kevin catching a bike tire as it's rolled to him. So that's demonstrating he can be reactive. The latency is low enough. It's not zero latency, but it's low enough that he can react to things in the environment and his actions, he can time, a swing of the hand with opening the gripper to throw objects. And in the bottom, you're seeing him in this current time manipulating a rope. And so it really helps to have sort of an intuitive one-to-one motion of your hands in order to tally out deformable objects in that case. There are challenges with developing a teleop system for a humanoid. First, line of sight is a challenge. So if you weren't wearing the VR goggles and you were just going to stand next to your robot and observe it, then you wouldn't have so much latency to be the problem because you'd be able to see things in the real world. But there would be problems with occlusions. The body would often be blocking the interesting parts of the manipulation task, or if you're reaching into a shelf or a bin, you just wouldn't be able to see. So our decision there was to have the operator actually look through the robot's own cameras and get a point of view from the robot. So that's very good. And a side benefit of that is that the teleoperator's information is limited to the same information that the policy will have. So they're not able to maybe use some line of sight view that the policy would not be able to observe when it was running. Although we believe we developed a very high performance teleop system and we can do a lot of tasks with it, there are inherent limitations through this technique. And there are some challenges and it does require practice. So one issue is lack of non-visual cues, no touch, force feedback, haptics. You're teleoperating in the air with trackers, so there's nothing attached to your body giving you a real feel for what the robot's feeling. In this case, he's within the same room, so if he touches something, he can hear that. But if you were to be more remote or if you were, in a noisier room, you might lack visual cues. Audio cues, though, are really helpful for a lot of manipulation tasks. It's amazing. The policy, though, of course, would not have those cues right now. A real challenge with Teleop is that the controller is essentially reacting to you. It's trying to mimic what you're doing. And so that can be challenging. I'll go into a little more detail about that. What is he seeing in his VR goggles? He's seeing a reprojected view of the stereo images in his headset. So it is a very 3D immersive. It's like watching a 3D movie at the movie theater where you feel like you're in the world and you feel like you can just reach out and touch something. You get these really strong depth cues. And it's rendered such that if you move your head around, you can sort of look up and down. So the robot actually doesn't have a neck pitched off, but it's sort of this big window, this 3D window in front of you. So you can sort of look down. It's like you're looking out into the world. We use these augmented reality overlays of the devices. So you're either wearing gloves or you're holding controllers, and those get retargeted onto robot grippers. And we render those grippers, you can sort of see in the image there as these green ghosts. And a nice feature with those is that they move sort of instantaneously. So it's like playing a video game. You're refreshing the view at a very high rate, higher rate than the robot's cameras are coming back. So you get instant feedback about where you're moving. And it's like a carrot on the stick. You're leading the robot. It's going to catch up. This helps minimize the sort of act and confirm pauses. So you don't have to move and then wait to see if the robot moved where you are. You can sort of guide it with the green avatars, and the robot follows you very well. So with practice, this is very intuitive, and you can do some very sort of dynamic manipulation tasks, in fact.
I just saw the three finger can switch around to a different configuration, right?
Yes.
And it just flip the thumb over.
Yes.
How does he control that?
We have a few control modes. One is if you wear gloves, 5-fingered gloves, and then we retarget that to a 3-finger robot gripper. But what he's doing here is he actually is just using VR controllers, which have a buttons and a trigger interface. And the trigger is going to just servo between an open pose and a closed pose, and the buttons cycle through different grasp modes. So you can sort of have a parallel mode or a curling mode or a flat palm hooking mode like that. So that is one option. From the policy's perspective, it doesn't know or care. It just sees finger positions and it's going to learn finger positions. So it doesn't care what sort of grasp mode you may have selected. We think the gloves are great. They're very dexterous. You can really do a lot with your fingers, but they're a more complicated device, and there's a lot of tasks you can accomplish just with the controllers. So we have, this is using PC VR. So we have a desktop that we run software on there called the Teleop client. And the Teleop client is in charge of sending commands to the robot. And those commands are, again, coming from the 6-point sort of one-to-one tracking. And those go to the robot, which is running MPC, which is at a higher rate. It's going to track these set points that come in. So to take a closer view of the system, on the right here, we have the robot running its MPC control and a piece of software called the Teleop server. And the Teleop server is going to help convert these Teleop commands into specific commands for MPC. So the robot over the wireless network is going to send robot state, which is both the state, the kinematic state, as well as the images to the Teleop client. Teleop client is going to use your body's motion as recorded through the trackers to send back a data structure that we call the client request. So here's a rendering of what the client request is. It's a pretty simple data structure. It's the finger positions of the gripper. It's the neck position of our one-DOF neck. And then it's 6-DOF poses for the hands, the feet, and the body. And it's going to turn out that that's the same as our action space. So let's look and see what the hardware and controllers are capable of. On the left, we're looking at our model predictive controller, which has been developed at Boston Dynamics over the previous 6 to 7 years. And it's been, shown to be incredibly capable, as demonstrated in our series of parkour videos. It can run, jump, backflip its way through an obstacle course. But MPC has limitations. And one of its biggest limitations is it can do all of these amazing things given an accurate state estimate and model of the world. But if it can't have that, then MPC can't really control the robot as well. So nowadays, what we're seeing is reinforcement learning-based controllers, which are going to be trained in sim and then transferred to real. So this is work on Atlas in collaboration with the Robotics AI Institute, showing our recent work on deploying RL controllers on Atlas, which have been very robust and can do a lot of interesting behaviors, even in the face of rich contacts that MPC would have been, you'd have to explicitly model them in MPC. All this video play a little bit longer so you can get to the dancing. All right. So MPC excels when it knows what it wants to do in the future. So if you give it a future horizon of desired actions, MPC can plan and choose what to do right now to achieve that future. RL tracking policies, similarly, and sort of implicitly know what they want to do in the future. But the Teleop system is more reactive by nature. So this video that's playing is showing Kevin doing 1-foot balancing. Now, if you just want to track end effectors, you can be quite fast and have a very low reaction time. But when it comes to the feet, you can't just instantaneously pick up your foot. You sort of have to know that you want to pick up your foot in the future and then lean and shift your weight, and then you can pick up your foot. So that's just an inherent limitation, and we address that through having a delay line added to the feet. So if you pick up your foot, we detect that through the tracker, and we have to, for MPC, convert that into a sort of contact mode change of a liftoff, and then there's going to be a swing and a touchdown. And you need to tell MPC either to stand forever on one foot or to touch down in the future so that you can sort of fall into your touchdown. So we do need to add some delay there. Once there's a liftoff, it can more instantaneously attempt to track your foot and try to get a precise touchdown location. But you will notice that when he lifts off in the video, the robot's going to take just an extra 500 milliseconds before it tracks you. So far, we haven't found this to be a major limitation in order to accomplish locomotion and manipulation tasks. The hands are tracked very quickly. You just have to sort of step into place and the robot will catch up and then you can go in with your hands. We definitely want to improve that. And we think that RL systems are going to offer a tool to be even more reactive and faster and sort of encode more motion predictive data inside of them. Okay, so we've used this Teleop system and now we can record human expert demonstrations. Let's talk about how we can use that data to learn autonomous behaviors. It starts with the data pipeline, which is going to take robot logs, which contain Teleop data from a Teleop session. And we're going to extract the data from those logs and store it in a format that's more suitable for efficient ML training. We store that on the cloud. We have a data set management system that we've designed and built. We call it our data pipeline. And this is really important because you have an ever-growing data set and you need all your data to be tagged so you can do searching and filtering and use that to build data sets and do your science experiments with your data sets. And the end result is this enormous amount of data, which is essentially pairs of observation and action samples. In our case, it's at 30 hertz. And a sample is going to be composed, an observation sample is going to be composed of the images from the left and right cameras, the proprioception, that's the robot state, as well as the actions taken by the teleoperator. Those are actions into the future, sort of a selection of actions paired with the observation that preceded them. Algorithm overview, we've just seen that previously in Ben's talk, but this is a supervised learning problem. Going from the observations to the actions. And the architecture that we're using is very similar to that published in TRI's LBM 1.0 paper. It's a clip VIT that's going to encode the vision and the language, and then we're going to concatenate on our proprioception data to create a conditioning vector, which goes into our diffusion transformer, which is going to iteratively denoise noisy actions into the actions that we're going to predict. And we're going to call this an action chunk.
So the action space there is the same as the Teleop?
Yeah, I'm going to show that right on the slide. Yep, but you're right, which is sort of a key design detail for us. So first, our observations and our actions contain robot frames. So we have to think about what frame should we express these values in. Well, the robot's going to be walking around and navigating, and it's not just stationary. So we probably shouldn't use a world frame, which could sort of have an arbitrary origin. So we use a body relative frame that we call stance ground. It's essentially a function of where your feet are sort of projected and flattened onto the ground. And we think that the proprioception data is also an important detail here. The robot is doing everything just from its head cameras. There's no sort of third-person scene camera that can give you additional observations. And so there's times when the hands and feet might not be observable in the image, so it can get some of that information through proprioception. But occlusions and partial observability still are a real problem for this. So when you collect data and design tasks, you need to make sure you do it in a way that the robot's cameras are looking at the information that it needs to be successful. A point here is that the policy is ultimately learning the closed loop dynamics of the robot and the controller. Your Teleop actions at the time that they were recorded are sort of completing the task successfully, and that's a function of how those actions were actually executed by the controller at the time. So if you were to change your controller in a significant way that changed these dynamics, then that's sort of like changing your robot. So you can think of that like a challenging multi-embodiment problem. Here you can see the data structures that represent the actions, and you'll notice that this just is the same as the Teleop actions. And as Ben said, the actions and the observations, the proprioceptions, they're all or very, very similar. In our case, with the full humanoid, this works out to being 60 dimensions. So it's not small that the network has to predict an action chunk of. All right, let's look at the task that we've been sort of demonstrating this on. So we call this the spot workshop. So it's a variety of tasks where the robot is manipulating these parts coming off of a spot robot. So here it's picked up a spot leg. It does some regrasps and then folding of the articulated leg. And then it's going to find a spot on the shelf and sort of reach into this constrained area and place it down. It's stepping to turn to face the shelf. And then it's stepping to come back and stand in front of the cart again. And now it's grabbing a spot faceplate part and going to crouch down low this time, pull out the bin, place the part in. On the right is the sort of the empty parts task where it's got this blue bin that it can open and empty. And then when it's done emptying it, it sort of pushes it away and it can recognize the goal state. And throughout, it can be reactive to changes. Of course, only reactive within the training data that it has seen. We can also do this in a multitask language conditioned way. So this video is showing the same tasks, but this time we've taken all of those episodes and put them together with language annotations, which you can then prompt through a natural language to tell it what to do next. There's no changes needed to the learning algorithm here. It's just the way that you put your data training samples together. It's sort of generalized and works this way. What's different is your data collection strategy. You need to make sure there's a way for these different tasks to sort of one flow into the other so it can have transitions in between. And anytime there's an ambiguous thing of, well, should I keep doing parts or should I turn around here and look for the blue bin? That's where the language comes in. The language is telling you what to do. Language is fairly high level. It's not going to tell you where to put your hand. That's all still coming from the visual motor policy. So I'm going to show you two examples of emptying the bin here. And in this first one, there's a bit of dirty laundry. This is what a failure often looks like. So it's crouching down, going for the grasp, but it's coming up short, emptying the gripper, and just keeps retrying. In this case, it sort of tried with the right hand, and then it decided to try with the left hand. But it's coming up short. And then on the right, we have a similar scenario where it's now this time it's able to just get that extra centimeter or two and get down low. So what's different between these two evaluation tests? It's really just the data. No algorithm or code changes were done. We just collected more data, more examples of crouching down low, and that helps. So the lesson here is what to do if the policy is failing in part of the state space. Well, the obvious thing is you should just collect more data in that regime. That's maybe not the most satisfying answer. Maybe you want there to be an algorithm change or something like that, but you should definitely try to saturate your task performance just by collecting intentional high quality data so that you can really see the full capabilities of the learning algorithm on quality data before you start looking into sort of other explanations or other approaches. How does the policy take steps? So in this video, Russell is going to place a part on the ground, and we're hoping the robot's going to see that and decide to go step over and pick it up. So it's going to move the bin away and then stand up and take some steps and grab it, and then walk back over and place it, and then continue. Again, this is not like emergent behavior here. This is training. There was training samples that showed how to do this. But how exactly is the robot able to take steps? As you've already seen in the action space, the feet are just SE3 poses. So is there any difference between moving the end effectors and the feet? And the answer is it depends who's asking. From the policy's perspective, it's exactly the same. It's just predicting trajectories of foot poses, and the robot just walks. That makes sure that the learning problem is nice and simple and general. It's just part of the action space, and the policy can learn to predict it. But from the robot dynamics and controller, it is very different. So especially with MPC, it has a sort of contact sequence that it's following. So you have to have something robot side that takes this stream of poses and tells the robot it's time to, break contact with your foot and go through a swing phase and make contact with your feet. So we have that on board the robot in this thing called the Teleop server, and it's able to take a stream of foot poses and convert that into a gait, essentially, which has been cleverly engineered so that you can be very reactive and you can move your feet in a lot of fast ways. And the robot will try to track you precisely, but it won't ever get confused and fall over or hover its foot. It'll do the right thing. So this was a pretty important engineering design to get right when developing the Teleop system. Another important thing I would point out here is that sort of gate stateness is on the robot side, sort of downstream of the policy. On the Teleop side, we want to enforce statelessness. You could have a lot of different interesting modes and drive modes in your Teleop system, but that would all be information that the policy would then have to predict and tell the controller to change modes and do all of that. So we choose to hide all that complexity more in the robot controller. And what this means is that essentially the controller can handle teleop and inference actions the same. It doesn't really know or care if it's teleop or policy. I wanted to highlight, we do some of this work on our manipulation test stand as well. So this is just like the upper body of the Atlas. And this is sort of our workhorse test bed for doing a lot of science experiments, rapid data collection, and test new ideas. It's effectively identical to the Atlas R1 robot, but without the legs. It runs the same software. It's got the same sensors on the head, the same teleop system. Everything is the same, which is very nice. And all of our pipelines and algorithms work just the same on MTS. So that's been a nice tool to have in our arsenal. And in this video, every sort of different task demonstration is all one policy, a multitask policy trained on all of the data together to accomplish all of these different tasks. All right, let me go through some lessons learned now. So we believe high quality data is the most important thing. We've heard lots about the data pyramid now, and the top is sort of where this work is presenting. If you have bad data, you're going to get bad performance, even if you have some fancy learning system. But if you have good data and a scalable learning system, which is able to ingest all the data, then you can get pretty good performance. A key thing here is that we're essentially programming behaviors through data. Bad data is like bugs in your program or like a poorly optimized program. You need to think about what you're training on and correlate that with the sort of performance you see at evaluation time. But collecting high quality data is hard. One, because it's hard to define. You can't just tell your demonstrator, collect good data. They need to know what that is. If you're doing like an image annotation task where you're trying to draw a bounding box or masks around objects, that's well defined. You can just tell them, make sure the bounding box is tight and all of that. But if you're saying empty this bin and do it good, like what does that mean? So you really need to think about the tasks and think about robust manipulation strategies and collect data in consistent, uniform ways that have sort of inherent robustness built in. So that's a big part of it, and that comes through the iteration cycle. When you do try to scale up data collection, you're going to get some bad data in there, maybe a lot of bad data. Maybe your instructions didn't come through, or you have different people doing it and they interpreted your instructions differently. So being able to look at your data and do quality assurance and tag it and mark it and label it is a really important part to building these data sets that are sort of curated data sets. Also know that data sets aren't static. The most direct way to improve performance is just collect more data. If you only collect successful demonstrations, policy will inevitably fail, and then it'll have zero examples of what to do, and it'll just look like really stupid, and the policy doesn't know anything. But that's because you haven't told it. So if you do, you need to expand your data set with recovery data, and there's a lot of tricks to doing that right. You can't just add a bunch of data and then suddenly it gets better. You have to be intentional about it, and you have to look at your data and sort of think about what it is you're asking the policy to do with its observations. It's also really important to have a fast science iteration loop here. We we collect and then we train and then we evaluate. And only after evaluating and sitting around and watching the robot and scratching your head, that's where you get the ideas of what you need to change, and you change that through collecting more data. So you need to make sure that iteration loop is fast. And you do that through good engineering, good infrastructure, good pipelines. That's really, really important stuff. This work of learning from demonstrations is just very empirical and experiment based. We have lots of ideas that we want to test, and we have way more ideas than we have the time to test it. And when you do test it, you need to be able to draw strong conclusions and not confuse yourself. The learning code, therefore, is really only 10% of the work. There's so much more that goes into this project that I didn't highlight in this talk. You're seeing a screenshot of our data quality assurance tool and annotation tool. All of the data infrastructure, the pipelines, the database systems, the visualization tools, the evaluation workflows. It's all really important. And evaluation is hard. Evaluations take time. They take time on the robot that you could have been using that time to collect more data, but instead you're going to use the robot to do evaluations. But you need to do a lot of evaluations from different initial configurations. And if you're not careful, your evaluations have high variance, and you might not actually learn the right things from your evaluations. So we do think simulation is very important. We use simulation to do quite a few of our science experiments and evaluations, and therefore we've also invested in our simulation stack and our simulation tools. Our sim runs exactly the same MPC controller. We can also run our RL controller in our sim, and it runs the same Teleop system. So we will do human Teleop just like you would on the hardware. We'll do that in sim, collect sim data, and we think that's very valuable. All of the code between sim and real is essentially shared, so you can also catch performance regressions. There's all sorts of good things you can do with the simulation. Some challenges here. Like I said earlier, the policy relies on the closed loop dynamics of the robot and the controller. And so if you change one and you have data that you collected a month ago and you've changed your controller, you might have just invalidated your data, or worse, you might have just introduced a performance regression and you don't really notice that it's just sort of degrading over time. So how can you improve your controller, especially with RL, where it's this rapid thing, like you can train and deploy a new RL controller? How can you do that without invalidating your data? There's a lot of variation potentially between robots, different camera calibrations, different kinematic calibrations, or robots will fall on the ground and take a slam and maybe be a little bent out of shape. We have had success transferring these policies between robots. We definitely don't want to be in a regime where we're stuck on, oh, it only works on this one robot. That's no good. So we do that through image augmentations and careful calibration, and that's important stuff. We think wrist cameras can help give more sort of local information. We're currently doing this from our head camera only. We think part of the answer is potentially the wrist cameras. Another challenge is that the Teleop system doesn't actually drive the robot at its physical limits. I talked earlier a little bit about some of the challenges to designing a Teleop system, but also to get really dexterous and do small, fine manipulation. These are hard things to Teleop. We think MPC and RL can do a lot more. And we've seen examples, even in RL, of some early examples of manipulation learned in sim and transferred to real, where it does amazing things, has these finger control policies that it would be fairly hard to Teleop, even using the glove trackers. So how do we solve tasks that are possible for the robot hardware, possible perhaps for the robot controller, but still difficult to use Teleop? We probably need to move beyond just Teleop-based action data. So for our next steps, we want to continue scaling this system because we know this works and you can add more and more tasks and do more and more things. But we still will have limitations that need to be addressed by exploring other parts of the data pyramid, whether that's cross embodiment from other robot hardware, simulation, UMI style, or human ego, or even third-person YouTube videos. There's lots to explore. And we also want to close the loop on policy rollouts to improve performance, whether that be through things like Dagger or offline RL or online RL on top of BC. All right, so that's the end of my talk. I'll acknowledge the great work by the team. It's a great team. This is Boston Dynamics and TRI collaborating together. And with that, I can take any questions.
regarding your Teleop, if I understand correctly, use MPC under the hood to track the high-level forces given by the motion tracking of the human, right?
Yep.
I'm wondering, is that because traditionally MPC has been a choice, or have you tried RL with imitation laws as a way to track their what has been your?
Yes, we are doing Teleop on top of RL now. All of the results that were in this talk were on top of MPC. We started at a point where we already had an incredibly high performance controller through MPC. I think MPC still remains the best. I don't think it will for long, but one of the key features that MPC gives us is the ability to have very high precision end effector tracking, even while the robot is in these very awkward positions. So you can squat low to the ground and you want to pick that one thing up off the ground. MPC will do that. I think RL will struggle to accomplish that, but it'll definitely come. And we're already exploring what it can do in our lab.
For certain tasks such as the one where you're picking up things out of the bin and placing them, how like prescriptive do you have to be about the exact flow? For example, using the right arm first before the left arm to place, or when you do a cross-body place after like recovering to pick up the part from the ground, placing with like the left arm.
Yep. For some tasks, we are more prescriptive, and I'd say that's mostly because we know we're going to collect a limited amount of data, so we want to limit the variation and only we try to be very intentional about the variation that we put in. For this specific task where it's left and right, we gave no instruction and we encouraged them to do whatever felt natural at the time. And so sometimes they would come in one-handed and empty, and then as you're bringing that hand in, you'd come in with the other hand and maybe do a double. And they just did whatever they wanted for that. And we were able to collect enough data that the policy just sort of chooses. It's pretty cool to watch it in that case. Whereas picking up from the floor, for example, we wanted to show that it could do that. And within about, a few days to a week, we collected that data, but we definitely needed to sort of limit the variation in that so that we could get good performance from a limited amount of data. But from there, you could continue to expand it so that it doesn't need to be so prescriptive.
And when you did need to be more prescriptive, I guess, what were the failures looking like? Was it like getting stuck switching between two modes, or just
that is a risk. I'd say that is a challenge of sort of low quality or poorly curated data, is that you can see it sort of do hesitations. Typically, it won't hesitate between arms. Once it sort of begins to move an arm, it's now, especially with the proprioception and the visual state, it's pretty locked into using that arm. But one interesting thing is like if it's going to pull the bin back into place, there's some point at which the bin is just far enough that maybe it wants to pull it in, or maybe it just wants to do a grasp, and it might oscillate between those two until it sort of commits to one of them. Yep.
Can you talk a little bit about, you talked about the importance of your judgment in choosing what data to collect and how to collect it.
Yeah.
That sounds an awful lot like cost function engineering to me.
I would agree. It is an art form. I hope with large data scale that this goes away, but for now, that is a reliable way to get good performance, is to give it the right data, which does require an expert to sort of observe how the robot is failing and fill in data. You could compare it to cost function engineering or reward engineering. I think it might be a little bit different. There's the dagger concept where you're supposed to let the policy fail, and that sort of leads you to data collection. So we think of it like dagger. Sometimes I'll call it almost like outer loop dagger. We both do the sort of traditional mode where you interrupt and correct it, but you can also just sort of see where it's failing and then intentionally collect failure cases. But there are some tricks to collecting failure cases intentionally, because if you have to intentionally fail, that means you have some window of actions that you actually don't want the policy to learn from. So you can label those.
So you showed on the data pyramid, quality versus quantity. Do you think that just collecting a ton of data, including garbage data and good data, is going to result in the robot being...
I think the TRI team has more experience under their belt of doing these fine-tuning experiments, and they have ongoing fine-tuning experiments with this Atlas data set. This data here is trained just on Atlas data. It doesn't contain the big pre-training soup data. But I think there's a lot of benefit from that. And at this conference and the previous one, we're seeing a lot of people exploring this space. I think what we're doing here in this work is sort of like phase one of a multi-phase thing, where we want to know sort of the absolute performance and capabilities on certain tasks. This isn't yet going for generalization. I think with the larger data, pre-training data, that's much more important for the generalization case. And that's going to be an important phase of this project, but it's not what's being demonstrated yet. Yeah.
If there's still time for a question. Yeah, I'm curious because you were mentioning that you were quite satisfied with the performance of the operation and in following, tracking the position of the hands. At the same time, you said that NPC is also problematic in reaching all possible dynamics.
Yeah.
Configuration. I'm curious, especially when grabbing things or grabbing things fast or heavy, would you say that you had to play with, for example, impedance that or the compliance that you have on the operation? How do you think about those things? How do you decide, for example, the compliance between the VR,
Yeah.
the controller and the gripper of the robot?
Manipulating heavy objects is still hard. So the view you're seeing on the left is from one of our earlier parkour videos. This is MPC showing off what it's best at. So in this case, it has a prior model of this heavy piece of wood. This is a very heavy piece of wood. And the robot's going to come up and snatch it, walk backwards, and jump and do a 180. This would be a lighthouse task for Teleop. I think we're looking at more at dexterous tasks right now, but heavy lift tasks are super valuable and important to us. And so we are going to work on those as well. MPC is quite capable of doing it if you give it a model of the object, but now you're back to more like state estimation of the object. But we know the controller is capable, but it's hard to communicate your intention that you're going to lift this. And before you lift, you need to sort of move your center mass back to counterweight. So that's still hard. I think RL will solve some of these problems over time.